Okay, hello, good morning, afternoon, or whenever you're watching this. We are in algebra, simplifying expressions with rational exponents and radicals. So the vocabulary for this week is actually really small, or at least it looks like it's small because we actually have um, a lot of vocabulary. So they're across multiple slides. So right here you see vocabulary. Go ahead and write this down. Rational numbers is any number that can be written as a ratio of two numbers, a over b, where a and b are integers and b cannot be zero, because when we have a fraction such as a over b, right, b cannot be zero, because what happens is if we have like a 1 over a 0, what you're really saying is you're trying to divide by 0, and that actually doesn't make any sense. That's what we would call the answer is what we would call an undefined. Because if you ever get to a point where you have a number being divided by a 0, it's not something that you can calculate. So it's an undefined. It's something that's undefined, pretty much. So that's what a rational number is. An irrational number is a real number that is not rational, right? So those are the two things that kind of like the two new pieces of vocabulary. Where I'm going to use a lot of old vocabulary words in here, and we're just going to use them in a different way. So the next slide, right? Exponent rules. These are the first rules that we're going to go over. Now, the first one is what we call a product rule, right? We're right here. Whoops. Undo. Okay. Okay, so right here we have the product rule, right? And the product rule just says that when multiplying two variables with the same base, you add their exponents. All of these rules, by the way, guys, are rules on how to deal with exponents under different situations. So we're going to go over each one of these exponents one by one, and then we're going to apply the exponent rules one at a time at first, and then a lot of them in one problem. So, just stick with me here. Make sure you write down all these examples. So the first product rule, right? Notice that we have the same base. Now, again, I have to remind you guys that in this case, when we have an expression like a number like a raised to a power, the a is considered our base, and the x right here, is considered our exponent, right? Just gonna abbreviate it as exponent, right? So when we have a situation where we have two numbers with different exponents, right? But they have the same base, right? We're allowed to add a shortcut. Is we're allowed to add the exponents, and it'll give us the same answer. So these rules, although they seem like a lot, they actually save you a lot of time in terms of simplifying expressions and calculations and all that stuff. They're basically shortcuts. So in the event where we have a raised to the x power times a raised to the y power, what we're going to do is we're just going to consolidate the variables. I mean, the exponents under one variable. We're going to have one new base, right? It's going to be a, and then we're just going to add the variables, right? Remember, the key here is that they have to be multiplying. If you notice here, right? This only works if you're multiplying between two bases that happen to be the same number. So an example of what this looks like, if x equals 5 and y equals 2, for example, right? What would this look like? Well, we would still have a, right? We still have our base raised to the fifth power plus another a. This one is being raised to the second power. We're just going to add them. What ends up happening is we have a 5 plus 2, right? Okay, so, and that gives us a to the seventh power. And that's it. If we remember that rule, right? Oh, sorry, there's a plus there. Let me just get rid of that. That shouldn't be there. They're supposed to be multiplying, right? Okay, so we are allowed to add their exponents, and nothing else at that point, right? So that's the product rule, right? So what happens if you're not multiplying exponents per se, but what happens if you're trying to divide the same base, but they have different exponents? What do you do then? Well, we're going to use what we call the quotient rule, right? Now, the quotient rule, when dividing exponents with the same base, subtract exponents, the numerator, and the the numerator minus the denominator's exponent. Now, in this case, order does matter because in the previous rule, it didn't matter whether X or Y went first because you're going to add them and you're going to get the same answer regardless. However, when you're subtracting, the order does matter, which is why I put specifically the numerator's exponent will go first, and you're going to subtract the denominator's exponent. If you happen to get a negative or whatever, there's other ways of dealing with the result, but it has to work out this way. Okay, so we're dividing the exponent with the same base. So if you notice, we're going to use a lot. So a raised to the x power divided by a raised to the y power. And the way we would solve this is we would just do a raised to the x power, which is the numerator's exponent, minus or subtract the denominator's exponent, which happens to be y. So if we use the same example as above, right? Okay. If we use the same example as above, if x is equal to 5 and y is equal to 2, then a raised to the fifth power, right, divided by a raised to the second power. We're just going to keep them under the same base now, right? It's just a. And we're going to subtract the exponents, 5 minus 2, which gives us our final answer. In other words, a raised to the fifth power divided by a raised to the second power is going to be a to the third power, right? If we were to add actual values to these, right? Like let's pretend a was 2, right? So let's see, we have a raised to the fifth power, right? Let's do 2. 2 raised to the fifth power divided by 2 raised to the third power, or second power, sorry. Right? That should be 32 divided by 4, right? And then 32 divided by 4 is just 8. And guess what? 2 to the third power, 2 times 2 times 2 gives me, hey, look at that, 8, which happens to be 8 to the third power. So I didn't even have to do all this calculation, to be perfectly honest. I could have figured out that it's 2 to the third, and 2 to the third is 8. I didn't even have to do the fraction. I didn't even have to do 32 to the fourth. This is why I say that these rules are actually shortcuts. Okay, so here, more exponent rules, right? Whenever you have a power, right? This time we only have one single base. Unlike before, we just have one. There's just one a right there. It's being raised to the x power, and then there's some parentheses around them. And then that entire thing, a to the x power, whatever that value is being raised to the power of y, right? So, right? So what does that mean? When you have a power raised to another power using parentheses, multiply both powers together. This time you really do have to multiply the powers, right? And it only works if you have parentheses around it. Like that should be your biggest clue. If you look and you see that there's parentheses, you know that you're probably gonna have to multiply the powers together, right? So again, let's do this example. If x equals 5 and y equals 2, then a to the fifth power raised to the second power is the same as saying 5 to the second power, which is equal to a to the 10th power, right? Okay, so that is a lot, right? Ultimately, this is like a shortcut to another shortcut. Because if you're wondering, like, well, what does this actually look like if I don't do the shortcut, right? Um, you end up with something like this: a to the fifth power squared is the same as a to the fifth power. Because remember, when we square something, it's just the base times itself, the amount of times. So we're squaring it, so it's times itself. And then we even though we have this, we're still forced to use the previous rule, right? We're still forced to use this rule, which means that we're just going to add the exponents. A to the 5 plus 5, a to the 10. So as you can see, this rule, the power rule, is actually a shortcut to another shortcut for a different situation. So it would help you a lot if you remembered it. All right, the next rule, power of a fraction rule. When you have a fraction raised to the power, distribute that power to both the numerator and the denominator of the fractional base. Okay, what does that mean? Well, we start with our fraction, right? We have a fraction a divided by b. Notice there's no powers, not yet. But the whole thing, the whole fraction is being raised to the power of x. Now, one thing that we should note is that every single variable always has a power. Every single number, even if we don't put it, always has a power. When we don't put it, the power is 1. And that matters in this case because what we're doing is we're distributing the power of x to all the exponents on the inside, meaning that x multiplies times the 1, anything times 1 is just going to give you, x or whatever it is, right? Whatever number you multiplied. And the same thing, for the other one below, which is why we end up with ax divided by bx. So let's put this in context. What does this actually look like when you have numbers, right? So let's pretend x is just 5, right? So we have a divided by b, right? Raised to the 5th power. The 5 goes to the a. The 5 also goes to the b. We end up with a to the 5th power divided by b to the 5th power. Now, notice they have different bases, right? There's an a, and the a is different from the b. Those are two different variables, which means we actually can't subtract them at this point. Maybe you were tempted to think, well, in the previous rule, you said something about when they're dividing, I had to subtract them, right? That's only if they have the same base. If they had the same base, you could have used a different rule, but they don't have the same base, therefore they're not the same thing, right? So we're not allowed to do that. If we knew what A or B was, we could probably reduce this a little further. If we knew what both of them was, well, then we wouldn't need the fractional rule. But this is just a way to make something a little less complicated. You're going to be using this rule quite a bit. So just, keep that in mind. Okay, so these last two are kind of just things that you need to know. Um, right, we have the power rule, the power of product rule. When you have two variables inside of parentheses raised to a power, distribute each power to each individual base. This is very similar to the fractional rule. The only difference is there's no fraction here. It's just like a and b. Like two variables are hanging out, they're inside the parentheses, and because they're inside the parentheses, both of them are going to get raised to the power of x. And they both have the power of 1 already, right? So when you distribute them, they end up with a to the power of x as well as b to the power of x. So again, in the example, if x is equal to 5 and we have a times b, parentheses, raised to the power of 5, the 5 distributes to the a, distributes to the b, right? And we end up with 5 a to the 5th power times b to the 5th power. Um, at this point, because the bases are not the same, we're not allowed to add the exponents. That is our final simplified form. That is the power of product rule, right? Okay, cool. So another thing that you should know is the zero exponent. You know, there's an actual proof for why this works. I'm not going to go over the proof just because time, but just know that the shortcut is whenever you see any number raised to the power of 0, your answer is always just going to become 1. Again, there's an actual mathematical proof for it, but you're gonna have to just take me on my word that every time you see any number, whether it's 5, whether it's 1,000, whether it's pi, whatever it is, if it's being raised to the 0 power, it's going to be 1. There's only a few circumstances where that wouldn't necessarily be true, but that's if it's in like a bigger problem, right? If it's by itself, then that's it. Okay, cool. These last two things are just kind of review. We kind of went over this last week. you should remember what a negative exponent is. If you have a to the raised to the negative x, you have to flip it, right? In order to change you're not allowed to have a negative exponent. Um, I mean, I suppose you are, but you have to change it into a positive. And what that means is that a is being whenever you raise something to the power of something else, you're trying to expand it. But if you're trying to raise something to the negative version of that, you're shrinking it, which is why we end up with a fraction here. 1 divided by a to the positive x, right? So if x is 5, right, we have a raised to the negative 5 power right here, right? It's going to equal 1 over a to the 5th. And a note about this, right? What if I have the opposite? What if I have this? What if it's already in the denominator? What do I do? You're going to do the same thing, except this is going to jump over here. So if you use the negative exponent rule and you want to turn this into a positive, the positive version of this would be a to the 5th power over 1. But since anything over 1 doesn't matter, right? It's just a to the 5th, right? This is important because this is going to come up in a lot of problems. You can actually simplify a fraction this way if the bottom of the fraction is a negative, right? You're allowed to put it to the top. That's going to be a very useful thing later. A fractional exponent, right, can be changed into a radical. This is what we did last week. You guys just practice going from exponent form to radical form, and you're going to use that again this week, right? Okay, so here we're going to move on to a problem. We're going to simplify each expression using exponent rules. So we're going to start right here. I know this might be a little confusing looking at it all at once, but this is where we're starting. Parentheses x raised to the 2nd power times y raised to the 1st power. Close parentheses raised to the 2nd power times, and then we have a radical. We have the quad root of y raised to the 4th power. Okay, so the first step here is to simplify one expression at a time. By one expression at a time, I mean this whole thing here is one expression, and this whole thing here is a separate expression. They're separated because you can see that there's a multiplication sign in between them. So it's kind of like having two things, right? We're going to focus on the left one. We're going to focus on the left one first, right? Whenever possible. Start from left to right in most math problems. All right, so we're going to start with the parentheses. And the best way, like we always want to solve the inside of the parentheses first, but because x squared and y to the 1st power they're different they're different what's it called bases, they're actually not compatible. So there's nothing we can do right now for the inside of the parentheses. So if there's nothing we can do for the inside, we're going to move out to one layer over to the outside of it, and we're going to focus on uh, that power, right? So remember what I said, that when the rule is, if you have parentheses and then you have the parentheses being raised to the another power, what are you going to do? Well, we're going to use the power of product rule to distribute the 2 to every variable inside the parentheses. And in order so I don't get confused, I'm going to separate the x and the y. So that's what I did here. I separated the x, I separated the y, and I distributed that 2 to that to the to the x squared and to the y to the 1 power. So what ends up happening is x squared times 2 times y raised to the 1 power times 2. And notice I didn't do anything with the radical yet. I haven't even touched it. I'm gonna just copy it over, and we're gonna focus on this left side of the equation first, right? Okay, so next we're gonna move on to um, step 2, which is using the power product rule to multiply exponent times the number of exponents. Each variable has an exponent. Okay, we already did that. Sorry, we're already on. We did that. We did that. Now we're moving on to step 3 right here, which is now focus on the radical, change it. So all I did here to go from step 2 to step 3 is 2 times 2 is 4, which is where I got this x to the 4th power. And then 2 times 1 is 2. I just simplified it. That's all I did. But I can't Even though I simplified them, I still can't multiply the x and the y together because they're not compatible. They're two different variables. So I'm going to leave them like that. And now I can focus on my radical from last week, right? So it's in radical form, right? I'm going to want to change it to exponent form. Why do I want to change it to exponent form? Why can't I just solve it? Well, we don't know what the base is. We don't know what y is. If we knew what y was, we could solve it because it's already in radical form. But since we don't know what it is, we're going to change it back to exponent form. So y to the 4 over 4 power, right? And 4 divided by 4 is just 1, right? Which is where this came from in the next step, right? Okay, cool. So now I have x squared times y to the first power. Now, could I leave it like this? I could leave it like this, but then I wouldn't be done. So the last step is, right? Since x and y's are different variables, they cannot be combined. That's something I've been saying since the beginning, but the two y's have the same base because they're both y's. So I can use the product rules and add the exponents. The 2 and the 1 get added together, right? Right, they came down from there. And now I have my final answer, right? I have x squared times y to the third. And again, the x and y are not compatible, so we can't combine them. That's as simple as it can get it. All right. Why don't we do another problem? One that looks a little different, one that requires the quotient rule, right? So step one, change the numerator and denominator from the radical form to the exponent form. So this is our original problem, right? Right here. We have as our numerator, right? Numerator is the top and the denominator is the bottom. The numerator is the quad root of x raised to the eighth power, and the denominator is the quad root of x raised to the sixth power. So we're going to change them from radical form because, once again, radical form is very useful if I know what that base is, if I know what x is, but I don't. So I'm going to change it to exponent form so I can use the exponent rules. Now, right here, I changed the quad root of 4 raised to the x power into this exponent right here. 8 divided by 6. Whoops. That shouldn't be that. Let's see. Okay, let's change that. That should be a 4. Okay, so 8 divided by 4. Then the next one, the denominator, right, is this one right here. That really is x raised to the 6 divided by 4, right? I remember I'm just changing them forms. We did this last week. So next, what do we do after that? Well, we already did this. We already did this step. Now we're going to use the quotient rule to subtract the exponents. We have our numerator, and our numerator has an exponent of 2. Since they share the same base of x, I'm allowed to use the quotient rule, and the quotient rule says that you can subtract the numerator's exponent. You can subtract the denominator's exponent from the numerator's exponent. So that's 2 minus 3 halves. Now the answer to that is just going to be 2 minus 3 halves is going to be 1 half. And the way that I figured that out is over here. Like if you notice this whole thing right here was me figuring that out. In case you don't remember how to deal with fractions when we're subtracting, we need to have a common denominator. Now, the denominator here on this side is a 2. The denominator here is a 1. If I multiply the top and the bottom of this left fraction by 2 over 2, I end up changing the 2 over 1 into a different fraction that's compatible, but I haven't changed the value, meaning 2 times 2, 2 times 1, right? 4 divided by 2 is 2. It's still the same fraction, right? This and this are the same. All I did was change it so that it has the same denominator, right? And then I just subtract the numerators. The denominator stays the same. All right, this is a review from my previous class from algebra 1A. So if you didn't take that class, this might be new for you. That's why I'm going over it. If you have, just skip over this part. So 4 minus 3 is just 1, and then you keep the 2, the denominator. Your answer is 1 half. Another way of looking at it is if I divide 3 by 2 in my calculator, I end up getting a 1.5. That gives me a 0.5, and 0.5 is what you get when you divide 1 by 2 in the calculator. So it checks out no matter what. Okay. All right, why don't we move on? Why don't we move on to something a little harder, simplifying the expressions. We have this expression here. It doesn't look that crazy, but it's actually a little more complicated than our previous ones. We have 8x raised to the ninth, and then parentheses 2/3. So what's actually going on here is the reason why this problem is different is we have 8, a whole number, times a variable raised to a power. That 8 is raised technically to the power of 1. It has its own exponent currently, right? It just doesn't affect it because it's a 1, but it has it. And whenever we run into this problem, the first thing we should always do is separate the bases, meaning that the 8 and the x have to separate, right? So that I can distribute the 2/3, right, to the 1 and to the 9. And in order to do that, we need to use um, the power of product rule, right? Because that's what that says. So we separated it. 8 is being now raised to the 2/3. Why? Because 1 times 2/3 is just going to be 2/3. And then we have x raised to the ninth power, parentheses, raised to the 2/3 power. That's a different rule. We're going to focus on just this for right now, right? So we're going to focus on that, and then we'll deal with the 9x to the ninth power later. So step 1 done. Step 2, raise each power to the base. And then reduce the 8. So we have, so I'm going to change it to a radical form, right? I'm going to change it to radical form so that I can solve for the 8. We didn't do this in the previous problems because we didn't know what the variable was. But in this case, we know that it's 8, right? So we're going to take the cube root, right? We're going to do this first. So what number multiplies by itself to give me 8? What number multiplies by itself 3 times? 3 times by itself to give me 8. That's 2, because 2 times 2 is 4, and then 4 times 2 is 8. And then I take that 2 and I square it, right? I do this one. I just kind of did it all in one step. 2 times 2 is going to be 4. So this whole thing reduces to just 4. Now that I know that I've reduced the left side to its simplest form, which is just 4, I'm going to focus on the right side now, right? I'm going to focus on this now. So step 4, how do we reduce this? We have to use a different power rule. Now we have to use the power rule because we have an exponent being raised to another exponent, so we have to multiply the 2 exponents. And when we have like a regular number like 9 multiplying by a fraction, really what it is, it's 9 over 1. So when we multiply by a fraction, we just multiply numerator times numerator, denominator times denominator. So we end up with 18 divided by 3. That's how I got 18 divided by 3. Again, these are the fraction rules, and this is something that I went over in my previous class. Now, 18 divided by 3 can be reduced to 6, which is where I get x to the power of 6. I just divided it, right, at that point. So now that we're left with just a regular 4, number times the variable x raised to the 6th power, all we can do is just combine them. 4 becomes the coefficient of x raised to the 6th power, and we're left with 4x to the 6th power, right? Just to be clear, that 4 still has the power of 1. And if I really wanted to be technical, I suppose I could add a 1 there, but I'm not going to because that makes it look like 16, And generally it adds to confusion. We tend to not put the 1 there, but it's there, right? So you can't forget that it's not there. All right, so why don't we move on to another problem, right? We have 64x to the 12th power raised to the 1/6 power. We're going to do the same thing. We're going to separate the bases. That 64 needs to be separated from that x so that we can distribute the 1/6, so we can distribute that 1/6 to the 64 as well as to the 12, right? So I used the power of product rule. So here we have 64 raised to the 1/6 power. times x to the 12th power being raised to the 1/6 power. Like with the previous problem, right? I'm going to change it to radical form so that I can take the 6th root of 64, which ends up being 2. I just did the math for you. It ends up being 2. Um, and it's already in the simplest form because 2 raised to the 1 power is just 2. So that's going to multiply by whatever this is, right? Now, we're going to have to use a different rule, right? We're going to have to use the power rule. So 12 over 1 times 1/6 equals 12 divided by 6. And, they can both, the top and the bottom can both be simplified further by dividing the top and the bottom by 6. So we have, 2 over 1, or just 2. This is my new exponent. This is where this came from, right? Okay, so then I'm left with 2, this 2, right, times x squared, and that gives me 2x squared as my final reduction, okay? So if it looks like I'm going through a lot of problems, it's because I am. Like, this stuff can be confusing, and the best way is just to be exposed to as many different problems as you can and practice them. All right, this is probably the most complicated problem, and I'm not gonna lie. When I did it at first, I got confused and I got the wrong answer the first time I tried this problem. I had to go back and I had to like really think about the power rules, and I missed something very important, right? So what makes this one different from the previous ones? Well, here we have a fraction, and that fraction is going to be an issue right here, this fraction. We have 1 divided by the 4x raised to the 4th power. Now, this is an issue because we have that fraction multiplying by x to the power of 12, right? And then that whole thing is being raised to another fraction and a negative fraction to boot, right? So there's like at least 3 or 4 rules that need to be used in this problem. And the confusing part is which one of the rules to use first, right? Well, the ideal solution would be to focus on the inside of the parentheses first, right? We want to reduce everything on the inside of the parentheses down to its basic form before we reduce the other thing. Now, the reason why I say that is because there's a lot to reduce. In the previous ones, we kind of just went with it, right? But here we can't necessarily do that, right? So we get rid of the fraction that separates everything from inside its own factors. So what I did was I said to myself, what's the best way to get rid of the fraction? What's the only way to get rid of the fraction? And the only way to get rid of the fraction, right, is to do the negative exponent rule. But none of these are exponents, I hear you saying. Well, that's true, but they don't have to be, because the negative exponent rule works forwards and backwards. So the really neat thing about that is I'm going to separate this, right, into 4 to the 1st power times x to the 4th power. And I want them to go up here. I want them to become part of my numerators. And the only way to make a denominator become a numerator is to change the sign of their exponents, right? So I hope you guys are following me on this. Um, but uh, what we can do is I changed the 4, right? I did one more thing I did beforehand, right? I changed the 4 into a base 2 squared. Now, the reason why I did this, you'll see in a bit, but it just makes things a little easier for me personally. So we have that, right? And in order to make them into the numerators, we have to use um, the negative. exponent rule, and we have to convert them into negatives. So what ends up happening is the 1, -1, right? But anything to the like 1 raised to any power is just going to be 1. So we don't even have to worry about this. There's nothing there anymore, right? So we have 2 raised to the -2 power times x raised to the -4 power. Now, if you notice this, right, is what we have here, right? Right. So that's how I got that. And that's probably the most confusing part of all of this, to be perfectly honest. It was this whole uh, reverse of the negative exponent rule. But now I have my negative exponents. Now I can hear you saying, why would you do that? I thought we weren't allowed to have negative exponents. Well, you're right. Normally we're not. But if you notice the power on the outside, the power on the outside is also a negative. And I know that I'm going to have to multiply the -1/2 times all the powers on the inside at some point, which means that those negatives are going to become positives, right? That's why I did all this. Okay, so am I done? Can I start distributing? Well, no, because I have this. You guys see where I'm at? I have 2 bases that are the same. I have 2 x's raised with different powers. I can add them, right? And that's what I did here. -4 plus the +12, right, should have given me, let's see. Wait, did I do, hold on, give me a second. Because I may have messed up. Right, right. Okay, so that's there, positive, negative. Okay, there it goes. And there it is. Okay, so what ends up happening here is we ended up with x to the power of 8. At this point, because these two combined into, well, this, right? Now I can distribute the -1/2 into here, right? -1/2 times the -2, that's what this is. And the -1/2 times the +8, that's what this is. And now we only have two bases. We only have the base of x, and we only have the base of 2 left. So we are slowly whittling things down. It's going to take a while. So let's focus on this one right here, right? So we have 2 to the -2 power times a -1/2. -2 multiplies by the fraction of 1. So it's negative, the negative and a negative become a positive, and we end up with a 2 divided by 2, which is going to end up being 1, right? So that's where this came down, right? Okay, so what about this side, right? What about this side of the multiplication? We have 8 times -1/2. Now, in this case, they're going to end up with a -8 halves, which is going to reduce to a -4. And now we have to use the negative exponent rule again. So now we have 2 to the x to the 4th power. And since we don't know what x is, we actually can't solve this. This is as simple as it's going to get. All right. So if your head hurts after that, mine does too. So um, you never really get used to it. You just get better at it. So let's move on. Word problems. All right, last section. Uh, background information. The approximate number of calories C that an animal needs in each day is given by the equation C is equal to 72 m raised to the 3/4 power, where m is an animal's mass in kilograms. In other words, their weight, right? So, problem, find the number of calories that a 625 kilogram bear needs every day. So what we're going to want to do is we're going to start with our equation that they gave us. Remember, they were nice enough to give us this equation, and we didn't even have to make it ourselves. But even if they had just given us the information, we could have probably made this ourselves. Uh, for now, step one is just start with the formula. All right, okay, cool. I have my formula, check. All right, so we have C is equal to 72, and then because M represents the animal's mass in kilograms, and we know that the problem says that they want to find out how much calories a 625 kilogram bear is, we replace M with 625, right? Cool. So we plug it in. Next thing we do is since we know what the base is, we're going to change this into radical form, right? And we're going to take the quad root of 625, right? We're going to take the quad root first to reduce 625 into 5, right? And then we're still focused because we're focused on the inside of the parentheses first, right? We're still figuring that out. We're going to raise 5 to the power of 3, right? And that gives us 125. At which point we're going to multiply by 72, right? Because it's just the last things that we have. And our C is equal to 9,000. Now, I'm not done. This is a word problem. The word problem says, find the number of calories that a 625 kilogram bear needs each day. A 625 kilogram bear needs 9,000 calories a day. I need to put it in a sentence to make sense of it, right? This is just a habit that you have to do. It's a way for you to show me that you understand what your answer means, right? Because if all you did was write C is equal to 9,000 without showing me your work, I'm not going to give you credit. And if you just, even if you get all the steps right, I still want to see that you understand what it means in terms of the actual problem. So make a habit of writing your answer in a sentence when you're responding to a word problem. Okay, word problem number 2, second example. All right, we're going to use the same equation from the previous problem, right? We have problem, a particular panda, right, consumes 1,944 calories every day, each day. How much does this panda weigh? All right, so is it even possible to figure this out with our current formula? Yes, it is. All we have to do is substitute the amount of calories, which is it's C, into our formula. And this time, we're just going to be solving for M because we want to know the animal's weight, right? So it's going to look a little different, right? We are going to definitely start with the same formula from the previous problem. C is equal to 72M raised to the 3/4 power, right? Cool. We're going to fill in what we know. So we're going to replace C with 1,944. All right. So far, so good. Now, we have 72 M raised to the 3/4 power, which means that we need to isolate M. Again, this is all from Algebra 1A. But when we want to isolate M, we want to get rid of everything around M. Now, we could try getting rid of the exponents, but it's easier to get rid of the coefficient first, which is 72. So I'm going to just divide both sides by 72, right? That way I can get the 72 out of there. 1,944 divided by 72 happens to be 27. So 27 is equal to M raised to the 3/4 power. All right. So I haven't told you guys this yet, but how do we make an exponent, a fractional exponent? How do we cancel out a fractional exponent? Well, we're not necessarily going to cancel it out like we would normally do in an equation. What we're going to do here is something a little bit different, but the similar concept. We're going to multiply it by its reciprocal. Now, the word reciprocal just means, like for example, 3/4. When I multiply it by its reciprocal, it just means that the denominator becomes the numerator and the numerator becomes the denominator. And what ends up happening here when we multiply them, we end up with the same number on top and on the bottom, which will always reduce to 1. And if you reduce a power to 1, you're basically canceling it out, right? So what does this mean? Now, what this means is in order to get rid of that 3/4 power on the M, we're going to have to raise M to the 3/4 power to the power of 4/3. It's reciprocal. And if we do that to the right side of the equation, we have to do that to the left side of the equation, meaning we're going to have to raise 27 to the power of 4/3. All right, that's where things get interesting because 27 raised to the 4/3 power, we're going to have to turn that into a radical form. 3 on the outside, 27. Reduce that to the cube root of 27, which is 3, raised to the fourth power, which is just 1. What happened to the other powers? Well, this whole thing here is this situation, right? When you raise a power like 3/4 by its reciprocal, it ends up becoming 1. So really, this is all m to the first power, right? Yeah, okay. So if you're confused, like word problems are something that doesn't always come naturally and it can be kind of difficult. But it's something that you should try to do. And it's something that you are going to be required to do at some point. So just give it your best shot and give me your best justifications. If you get the problem wrong, as long as I see that you were trying and you were giving me the steps and I can kind of tell where you went wrong, I'll still give you credit. But if you just write like I don't know and you don't even try it, then you're not gonna get credit. Like if you're struggling, you gotta talk to me, right? Email me, set up a Zoom appointment, or ask a quick question in the comments. Either way, guys, thank you and good luck.